So, as Kevin said, I study exoplanets, I look for exoplanets, I catalog the exoplanets, and I really want to know what's out there and what are these other worlds orbiting the nearby stars. So let me tell you a bit about the science and what is known about what's out there. The most successful method for detecting planets around other stars has been the precise Doppler method. It's the first successful method, and it found hundreds of planets, and only very recently has the Kepler spacecraft surpassed this method as a way of detecting large numbers of exoplanets. It takes a long time. This is, career-spanning work in some cases. The idea is that as a planet orbits a star, the center of mass between the two objects is not at the center of the star, it's displaced. And so when the planet goes around the star is in some sense executing its own small orbit around the center of mass. So the star wobbles back and forth very slightly due to the planet, but because the star is so much more massive, this is a very small effect. So the reflex motion of that star is what we seek to detect. It's very difficult to actually see a star on the sky with a telescope wobbling about with respect to the background stars. So far we have not yet discovered any planets through that method. The tolerances are just too high. However, the radial velocity of the star, the component of the star's motion towards you and away as the planet goes around, turns out to be just detectable. So for scale, when Jupiter orbits the sun, it makes the sun wobble once it goes around every 12 years, as Jupiter goes around it. The speed of the sun, about that 12-year circle that it executes, is 12 meters per second. So this is a very ordinary human speed. It's a little faster than the fastest people can run. The Doppler shift of the light coming off of the star due to that is very small, but it is just detectable. So the name of this planet hunting game, if you want to use the radial velocity method, is to make the most precise Doppler measurements of the Doppler shift of starlight that you can. And the more precise your measurement, the smaller the planet that you can detect orbiting that star. So to do this, astronomers use spectrographs to break starlight up into its component colors. This is a schematic of the Hamilton spectrograph at Lick Observatory, where I did a lot of my work. The idea is that the light comes in from the telescope at the top of this diagram. We collimate the beam so that we can play with it and disperse it. And then we use two dispersive elements in a shell grating, just these metal grooves on it, and then a pair of prisms to disperse the light in an orthogonal direction. Both elements basically work the same way. And then we have a large camera that images the resulting spectra onto a CCD chip. And this is basically what it looks like. So we've stacked the spectrum up. We've dispersed the starlight with the prism so finely that if we were to stretch it out at full resolution, it might go all the way around the room. We could start there and just go all the way around from red to blue. So what the prisms do is they stack all of the orders up like this. So you sort of read it like the book. The longest wavelengths of light that we're recording are in the upper left, and you just read all the way across, and when you get to the end, you start the next line. So this is the actual solar spectrum. This is data for the sun, taken with a shell spectrograph, and imaged on a CCD, so you can imagine there's about 4,000 pixels going across this image. We use these 2K by 4K CCDs. You'll notice all of the missing colors here, all of the absorption features. This is because the sun's atmosphere is cooler than the sun, a thin layer of gas right above the surface of the sun, and each of those absorption lines is due to a different atomic transition of some element in the sun's atmosphere. Most of them are due to iron. Iron has the most complex structure, but there's a couple others like the sodium doublet up here, calcium is down here. So from this we can find what the sun and the stars are made of. But when we're hunting planets, we've got all these wonderful lines and we don't care about any of that. We just want to know if they move. We just want to see the Doppler shift of these lines getting redder and bluer, redder and bluer. And we want to see it happen very subtly. We're looking for 1 meter per second precision, and we want to see if they go one way and then they come back every 12 years or so if we want to find something like Jupiter. So this is a long-term investment of your time to find these planets. For scale, 1 meter per second precision, which is about the state of the art, would result in all of the lines, if it was a blue shift, moving to the right, not by a pixel, but by about 1/1000th of a pixel. That's our current precision level. And we're working on improving that, but that's all we can do for now. That requires stabilizing your instrument or calibrating your instrument, and that's why this is difficult and why it wasn't successful until the mid-1990s. But we do it now, and we can do it almost routinely. Typically, if we look at a star, this is what we see. So you can get a sense here, what a graduate student career you're looking for. On this target, we measured this particular target about a dozen times for a few years. You can see the resulting Doppler shift that we measured in the stellar spectrum. And it's all basically consistent with measurement uncertainties. This star does not have a gas giant orbiting it within 5 astronomical units. Or an astronomical unit, it's the distance between the Earth and the Sun. So that star doesn't have anything within 5 times the Earth's distance orbiting it, any large gas giants. It could have a planet like the Earth. That measure, the Earth would induce an amplitude of 10 centimeters per second, so we wouldn't notice that. But there are no gas giants here. When you do notice something, you immediately apply Kepler's laws to try and learn what you can about it. To remind you about Kepler's first law, planets orbit the sun, or a star, in an ellipse, with the sun or the star sitting at one focus. So planets in principle can orbit in any kind of crazy orbit. They can have a circular orbit where the eccentricity, E, is 0, and a cometary orbit, so what the comets have, eccentricity of 0.9, just for scale, this is what an eccentricity 0.9 orbit would look like. The planets in our solar system, except for Pluto, like everyone else's planet, all have eccentricities of a few percent at most. So we expect mostly circular orbits. However, in principle, if you saw a planet with some other crazy orbit, something highly eccentric, you might get a different shape. So there are 6 Keplerian orbital parameters, which I've listed on the right there, but what I really want to point out is that if you have a circular orbit, that's this column of curves I've shown, you have an eccentricity of 0. You get a sinusoidal radial velocity response. This is just a simple sinusoid because the planet's moving in a circle. However, if you go to eccentricities of 0.3 or 0.6 or 0.9, you get a very different result. That's because from Kepler's second law, when the planet is very far from the star, it's moving very slowly. And it's accelerating very slowly because it's far from the star. If it's accelerating slowly, then the star, which is doing the same thing but smaller, and that's what you're measuring, is also accelerating slowly. So for long stretches of time, there's not much change in the velocity. And then during periapsis, when the planet whips in quickly near the star, the acceleration is strong and it happens over a small amount of time, and you get a sudden change in the velocity of the star. So by examining the radial velocity curves that we might measure of a star, we can deduce the shape of a planet's orbit. So here is some typical Doppler data of a star and a planet. Velocities go up, 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 and then over the course of a few months change by 100 meters a second, which is a very small amount, but for us it's very easy to detect. So there's a few things you can immediately tell about this planet. First of all, its orbital period, you can essentially just read off of the graph. Measure more carefully, it's about 2.2 years. The second is you can measure the amplitude of the curve that I've drawn through these points. And it works out here to about 100 meters a second. Given the orbital period of this planet and the mass of the star it's orbiting, that works out to a few times the mass of Jupiter. So evidently this star has a planet in a 2-year orbit. From Kepler's third law, we then know its distance from the star is a little more than 1 astronomical unit, and it's about 4 times the mass of Jupiter. So there's a planet around this star, but it's not like any planet in our solar system. It's bigger than our biggest planet, and it's much closer to its star than our biggest planet is to the Sun. But finally, this is not a sinusoid. And this pattern repeats very predictably, and it has done, it just keeps doing this. We have more data. And you can basically just read off by eye what the eccentricity of this planet might be. It's basically somewhere between here and here. And so the eccentricity of this planet is about 0.5. And so its orbit is just a little bit more circular than the blue curve here. We also know some information about the orientation of that orbit on the sky, which is what you're seeing in the different rows here, depending on how you orient the radial component compared to the shape of the orbit. So we can learn a lot about these stars if we know how far, or these planets. If we know how far from their star they are, then we know how bright, and since we know how bright the star is, we then know what the typical temperature on the planet is. So we have the mass of the planet, modulo a geometric factor. We know the temperature of the planet. and we know the shape of its orbits or how much that varies. So we've been doing this for a while now. The first planet was successfully detected with this method in 1995. So here are some overall numbers. About 6% of the ordinary stars that we survey, we've detected planets around. And for scale, if we were looking at the sun from another star system, we would just now be detecting Jupiter, because its orbital period is 12 years. So we want to see the entire orbit before we say we understand what we're looking at. So that means really 6% of normal stars have planets that are easier to detect than Jupiter would be around the sun. About 1% of stars have what we call hot Jupiters. That means when you measure the orbital distance, the period of the planet, the period turns out to be extremely short. They typically show up at periods of around 3 days when we see these things. So there are Jupiter-like objects orbiting their stars in 3-day orbits. For scale, Mercury, the closest planet to the sun, orbits the sun every 88 days. So these things are extremely close to their sun. They're just a few stellar radii away. Those are the easy ones to find, so we found them first, so we think about them a lot. The median mass of all of the known planets through this method is a little over the mass of Jupiter. It's about 1.7. So yeah, about half the planets we find this way are these super Jupiters, we call them. But another half are basically typical of the solar system. The minimum mass we can detect right now in special circumstances with this method is around a few times the mass of the Earth. The record holder is 2 or 3 times the mass of the Earth. So again, Jupiter is a threshold case because of how long we've been monitoring stars. Earth is almost the threshold case, a factor of 2 or so away, in terms of the mass at the orbital separation for close intervals. The median period is about 1 year. So we typically now find planets at orbital distances from their stars comparable to the orbital distance of Earth from the Sun. 1-year orbits are ordinary. And about 1/3 of the stars with known planets are known to have more than one. So when we see a planet, we want to characterize its orbit, we look at it, and we'll notice we can't get one smooth curve through there. We subtract the best fit, and we see another planet is orbiting the star. So multiplicities come, which is nice because it makes our solar system feel more like home. More common. So a lot of groups around the world employ this method and employ other methods to find planets. If you look at the number of discoveries by year, it looks something like this. When a planet's discovered is a little funny, so this is the first time a refereed journal article about the paper was published. So here we are in date. You can see in 1995, things really took off. That's when people really realized these things are real. We found 51 Pegasi b. And since then, yeah, it's just gone up. And who knows what 2001 will be, or 2011 will be again. So planet discovery rate's increasing. There are over 600 exoplanets known today. I was telling you about the orbital distances. This is a logarithmic orbital distance scale from very close in, 100th of the distance from the Earth to the Sun, an astronomical unit. 1/10 of that distance, Mercury sits around here somewhere at 0.2 or 0.3. At 1 AU is the Earth-Sun distance. It's a very typical sort of planet distance. And then out beyond about 4 AU, we're not really sure because orbital periods out there are so long, we haven't really probed them yet. So this fall off you see it for around 4 AU is purely a detection bias. For all we know, it could just keep increasing. Anyway, the two things you notice are that most planets are either out beyond 1 AU or they're piled up at about 3-day periods. And that's another detection bias, actually. Through the transit method, which I'll talk about in just a little bit, is only sensitive to very close-in planets. So we see just about any planet in the 3-day pileup. And we're not really sure why planets like to park themselves there, why planets are found in 3-day orbits, but it's an interesting feature of the distribution. At any rate, this was a big puzzle when it first started to be discovered, because we believe planets have to form out beyond a few AU if they're giant planets, and most of these are giant planets like Jupiter. We believe that there's no way to form one very close to the star, which means these giant planets who are forming out here somehow must be moving in. And this really upset our understanding of how the solar system formed, because all of our models essentially said they had to form in situ. They had to form right where they are now. And this is planets move around. So the theorists immediately said, oh, of course, when they wrote all the equations for why planets must move around, the problem is their equations all said that the planets just move, and just dive right into their star. So now planet formation theory says it's impossible to form planets. So something must stop them, and typically stop them at around 3 days. We're not really sure. The frequency in terms of the mass of the planets we're detecting, we're basically complete for monsters that are 10 to 20 times the mass of Jupiter. In fact, something that massive, 10 to 20 times the mass of Jupiter, may not even really be a planet. It may be some sort of failed star, some brown dwarf that was going to be a star and just never got enough mass to start fusing hydrogen and turn bright. But we don't really know how to make that distinction, so we keep track of basically anything up to around 25 times the mass of Jupiter. There aren't any. Most of the planets we detect, as you can see, are more typical of the solar system. They're around the mass of Jupiter or smaller. And our detection limit is way down in here inside this bottom bin. So the bin with most of the planets in it is also the only bin on this chart with any incompleteness. So most planets are like those in the solar system, like Jupiter or smaller. And we can look at all sorts of ways to chop up the data of all of the known exoplanets. This is a plot of the semi-major axis of all the exoplanets known and detected, and their orbital eccentricity. So from perfectly circular orbits, all of these points on 0 are, so far as we can tell, circular orbits. And then at the very top, you would have 1, and orbital eccentricity of 1 is not really a bound orbit. So it's the most extreme eccentricity. Comets have eccentricities very close to 1. And there's some interesting things going on here. All of the planets in very short orbits, almost all of them, have circular orbits. Turns out this is the effect of tides. When the planet gets very close to the star can distort the planet's shape. The planet can raise tides on the star, and because both of those objects have viscosity, they can dissipate energy, and that energy comes out of the orbit. The lowest energy orbit at a given angular momentum is a circular orbit. So whenever a planet is very close to its star, it should quickly lose all of its eccentricity through tides. And that's essentially what you see, except for a few oddballs. Although with the error bars, a lot of these are consistent. But further out here, we see something totally different. In the solar system, most planets live here with very circular orbits. So in this sense, the solar system is not typical, apparently. Most solar systems have modest eccentricities for their giant planets, unlike ours. What does that mean? Not really sure. But our solar system does appear to be special so far, and at least that way, with one caveat. If we were looking at the solar system, Jupiter would be 1, 2, 3, 4, 5 here. And we would have just detected it. And Saturn, Uranus, and Neptune would be out here. We can't see them yet. And the rocky planets inside, we wouldn't have detected yet. So it's possible there is a population of solar systems out there we just aren't sensitive to. But it doesn't look like we're going to end up being able on that. So I want to make a quick pitch about these plots and everything. I made these using the Exoplanet Data Explorer at exoplanets.org. Exoplanets.org is one of the many catalogs of exoplanets on the web. I like it best because I maintain it. And it only includes what I would consider to be robust orbital elements for exoplanets, as reported in the peer-reviewed literature. So if it's in here, it should be right. And it's not just out of a press release from somewhere. So it doesn't have every planet. You're not going to see, as soon as the press release hits, it's not going to appear in here, because we wait for publication, and then the undergrads have to come in and put all the numbers in and check them. It takes a while. So we're not fast. But we do have this amazing plotter, which I wish I could take credit for, but I didn't write it. It lets you make these plots. And you can do color scales, you can do asymmetric error bars, you can make histograms, you can make plots, you can make them log scale, you can choose whatever you want. It's a really elegant data visualization tool, and it's plugged directly in to the Exoplanet Orbit database. So you can make all of these plots yourself. It also has illustrations of the radial velocity curves for every planet. Each of these points is clickable, and will take you to a page that tells you about that planet. And there's also a sister site which has data from the Kepler spacecraft, so you can explore the Kepler spacecraft planets as well. Okay, enough self-promotion. This is a particularly interesting system. This is a lot of people's favorite exoplanet system. First of all, it's a very small star, an M-dwarf star, 0.4 times the mass of the Sun. Red, cool object, and it has a pair of giant planets orbiting it. This is the complex radial velocity curve that we get. The two planets are in a resonance. So one goes around every 30 days, and the other goes around every 60 days. And as a result of that resonance, the planets interact with each other in ways that we can actually detect. So this is not just the sum of a 30-day sinusoid plus a 60-day sinusoid. You can see that there's this envelope, this strange shape going on. And that's the result of the planets interacting with each other, which actually helps us figure out what their true masses are. What's actually going on is that they're not in circular orbits, they're in slightly eccentric orbits. And those orbits don't stay put. So Kepler's first law, planets orbit in ellipses, not strictly true, because another planet can perturb that ellipse. And in this case, the ellipses actually precess. And so the elliptical orbit of each of the planets precesses all the way around. That precession time is about 11 years. And that's what you're seeing here in this envelope. You're watching eccentric orbits precess every 11 years. So it's really remarkable that we can see this kind of planetary dynamics. What's even more remarkable is that if you get those dynamics right, and you subtract off and look at the residuals to this curve, underneath it all, there's a planet on a 2-day orbit that's 8 times the mass of the Earth. So this is a 3-planet system. But you can only get this one right if you do the physics right first to figure out what's going on with the giant planets further out. So this is evidently some sort of rocky, or maybe something like Neptune or Uranus even, but it's right next to this cool M-dwarf star. So that brings me to this. Oh, we have a question? No? Oh, okay. That brings me to this issue of why do we care where these things are, if they're close to the star or far away from the star? And one of the reasons is that we want to know what the conditions of the planets are like. We're starting to be able to find planets that are rocky, like the Earth, 2 times the mass of the Earth. That's probably a big rock ball. We don't know about its atmosphere yet, but we could say what its temperature is like. If you're around an M-dwarf star like this, you can be very close and still not be very hot. Now this planet is extremely hot, so very, very close. But the habitable zone, sometimes it's called the Goldilocks zone, around a star is the region within which, if you put the Earth there, Earth would keep its liquid surface warm. So it's just a way of thinking about, where could you expect something like Earth to be elsewhere in the galaxy? So for the solar system, you can't move Earth much closer to the sun. If we got much closer, then the delicate balance that keeps everything going on Earth would fall apart. We would lose a cold trap in the upper atmosphere that keeps water vapor from being able to go up high enough above the ozone layer where it can be dissociated by the sun's ultraviolet radiation. So there's a pretty delicate balance. We're about as warm as we can be on Earth without, over the course of 1 billion years, losing all of our water. We have for something like 4 billion years. But you could move Earth out pretty far. And if there were enough greenhouse warming, you could maintain liquid on the surface. Mars is just at the very edge of the habitable zone. You can't go much further beyond that and think about having liquid water.
So you're not just looking for planets, but you're looking for Earth-like habitable planets.
We would love to find Earth-like habitable planets. That, in fact, is the explicit goal of a lot of these space missions. Because you have to give it targeted. There's a lot of planets we could look for. That's the target. We want a mission like Kepler to find a rocky planet in the habitable zone around its star, so that we can then go study it further. We want to know how often it happens. Right now, we don't know how many stars have rocky planets in their habitable zones. A star with half the mass of the Sun, like the one I talked about earlier, that zone is much closer, which is nice because when a planet's closer to the star, the radial reflex motion, the radial velocities that we measure are stronger. And so it's easier to detect lower mass planets around lower mass stars like this. And it's even easier on very tiny stars. So if we want to find rocky bodies in habitable zones, we like to look at very low mass stars where those planets have to huddle very close to the star if they want to be warm enough for liquid water. This is sometimes called the Goldilocks zone because you can't be too hot, you can't be too cold. You want it to be just right. So I said that a lot of stars known have multiple planets in them. Perhaps one of the most famous is GJ 581 or Eliza 581. This star has a very complex radial velocity curve that's somewhat hard to interpret. In fact, the academic literature on this star right now there's a huge argument going on about the right way to interpret this very complex radial velocity curve. Right away, you see the curve they've tried to draw through these points. It's pretty complex. It's not just one sinusoid. You can see at least two there. You go over a longer period. There's a lot more than two sinusoids here. This is a nearby star. So D is 6.3 parsecs. This thing is about 20 light years from Earth. It's our neighbor. And it's about 1/3 the mass of the Sun. So this is a small guy. The habitable zone is with periods, I think like around 50 days or so. This curve, though, does decompose pretty nicely into 4 orbits. So there's one period that shows it pretty well at 3.5 days or 3.2 days. The implied mass of the object in that orbit is 2 times the mass of the Earth. There's one at 5.4 days. The mass has 16 times the mass of the Earth. There's a 13-day orbit, 5.4 times the mass of the Earth. And one out at 67 days, with 7 times the mass of the Earth. This last one is just at the outer edge of the habitable zone. Now it's 7 times the mass of the Earth at least, so it may not be a rocky object. If it is a rocky object, or if it has rocky moons, those moons are plausibly habitable, in the sense that you can have water. Now there's been a lot of arguments about this. There have been multiple press releases about this system and whether the planets are habitable. This was originally announced as a habitable planet, and then Jim Casting, who defined the term habitable zone, pointed out that they miscalculated it. It was outside the habitable zone. And then they revised the orbit and got a new period, and then it was back in the habitable zone. And there was a NASA press release that some astronomers have found 2 more planets, and one of them was around 50 days, and that is squarely in the habitable zone. And then a paper came out saying that they had done this analysis wrong and there was no such planet. So it's complicated. So you'll have a lot of press releases about rocky habitable planets around the system. I don't know the answer, but we're working very hard to find out. Yes?
Yeah, you said that your data implies the mass of the planet?
Yes. You're measuring the motion of the star towards you and away from you. So if the planet is orbiting like this with respect to you, then you're seeing the motion of the star, and you can measure the mass of the planet. But if the planet were to orbit this way, then all of the star's motion is perpendicular to the line connecting you to the star. So there's no radial component of the motion. So you only see the component of motion in your direction. So since star, there's no reason that there should be some conspiracy where all of the planets are face-on or all the planets are edge-on. They're randomly distributed. So you can say typically we'll be off by something like the median of sin I for uniform distribution, which is like 15 to 20%. So it's something larger than 7, maybe it's 8 times the mass of Earth or 9. But it's not going to be Jupiter mass unless we got extremely unlucky.
You said most of these are really massive planets. Is it possible that they have moons large enough to throw off this rotation as well?
We cannot use this method at the moment to detect moons. I've actually recently done this calculation, and I wondered if I had a Jupiter, or how did that? I think it was 13 times the mass of Jupiter, and its moon had 13 times the mass of Jupiter, and they were orbiting each other. Could I tell in the radial velocities because they'd be wobbling themselves? Barely. So even in that extreme case, it's not going to happen.
What about the retrograde of the planets?
We can't tell retrograde. So the planets orbit the star. We cannot even tell usually if they're mutually retrograde. And they don't always go around in the same direction the star spins. We know that, actually. But it's generally difficult to tell which way the planets go. We just see that. Yes?
When you were talking about planets,
moons, do you actually detect the combination of the planet-moon system?
Yes, we detect the massive combined planet-moon system.
Yeah.
That's right. So a powerful method that we use is the transit method, and this is what the Kepler spacecraft is doing to discover planets. In fact, it's explicitly spec'd to detect a planet like the Earth orbiting a star like the Sun at 1 astronomical unit. That's what it's supposed to be doing. This chart shows the brightness of that star as it's being orbited by that planet, and this is just an inset of what the planet looks like at any given moment. Now keep in mind, we're not imaging these planets, we're just looking at the brightness of the star. When the planet passes in front of the star gets dimmer during the time it's in front. We need to be pretty lucky to get this configuration. Most planets do not transit their stars. It's more likely if the planet is close to the star that you'll get this kind of a configuration. So for 3-day pile-up planets, it's about a 5% chance. And since we have a lot of searches for these sorts of things, we find a lot of those 3-day pile-up planets. The chances of something like the Earth transiting the Sun are very small. So you would have to look at a very large number of stars if you wanted to see one like the Earth, which is why the Kepler spacecraft is looking at 100,000 stars. Another thing you can notice here, when the planet's in the back half of its orbit, it's bright. And when it goes behind the star, the whole system gets very slightly fainter. Now, this is very hard to do from the ground. It's only been successfully done last year. But from space, there's a secondary eclipse when the planet goes behind the stars. And the Kepler spacecraft can detect that. The Spitzer spacecraft can also detect that. So, by monitoring the spectrum of the star-planet system just before the planet goes behind, you take a spectrum now and then now, right when it goes behind, and you difference the two spectra. The difference is the spectrum of the planet. So using this method, we can actually get a spectrum of an extrasolar planet and find out what it's made of. The other nice thing is that when it goes in front of the star, the amount of dimming you get depends on the size of the planet. So when you have a transiting system, you can use radial velocities to measure its mass without an ambiguity because you know its edge on. You can use the depth of the transit to get the radius of the planet, so now you have a bulk density for the planet. And you can see, is it like Jupiter, is it like Uranus, is it like the Earth? And you can get a spectrum of the planet to find out what its atmosphere is made of. So we really like transiting planets because they tell us so much about themselves. If you look at the spectrum of a planet, they're very hard to interpret. They're also very hard to get, so the James Webb Space Telescope will help a lot. This is an infrared spectrum of an extrasolar planet done by Mark Swain at the Jet Propulsion Laboratory. The black points with error bars are the spectrum he measured of the planet. The colored curves are theoretical curves of what the planet would look like if its atmosphere had different compositions. So he's trying different compositions to see what works. The purple curve is if the atmosphere is made of steam, and obviously doesn't work at all. The green curve is steam plus methane, and that doesn't work. But when he does steam plus methane plus carbon dioxide, he gets what looks to me like a pretty good fit given those error bars. So he's arguing that we know that this thing has water, methane, and carbon dioxide in its atmosphere. This is a giant planet like Jupiter, so those things are not surprising that they would be in the atmosphere. But still, it's nice to see that we can actually tell that these things are made of perfectly ordinary materials. Another nice thing about transits, and in retrospect an almost embarrassing thing about them, is that when a giant planet transits its star, it's actually not a really subtle effect. It's about a 1 to 2% dimming around pretty bright stars. And it's pretty easily detectable. I could have shown you the Hubble Space Telescope transit curve for this. This is the brightness of the star as a function of time, and over the course of about 2 hours, it gets about 1.5% dimmer. 1.5% is challenging to do from the ground. But the reason I showed you this is that Deeg and Garrido are not professional astronomers. And neither are Gaspario or Presti, who also measured it. These are amateurs using amateur equipment to detect a planet. And because it's much easier to ask an amateur with some good equipment to help us out than it is to go through months of asking for telescope time, amateurs have contributed importantly to determining the sizes of newly discovered transiting planets. So this is a scanning telescope write-up about these two fellows, and there were others that measured the brightness dip due to a transiting planet. And here is their data in Astronomy and Astrophysics, the professional peer-reviewed journal. So here's their data. Astronomers analyzed it and came up and determined that the planet is 1.15 times the radius of Jupiter. So this is the sort of thing that, in principle, you can do with amateur equipment and go discover a planet. There are so many of these things now that on any given night, you can actually find which one is going to transit its star that's visible where you are. So at almost any night, almost anywhere on Earth, you can find one of these things happen that's detectable with amateur equipment. So if you're interested in going down that route, there are transitsearch.org is really your portal to all of this information. Exoplanets.org will soon also have transit ephemerides. That's one of my regrets thesis to get all of that going based on the latest data. And the American Association of Variable Stargazers also naturally has been keeping up with these things because this is a new class of variable stars. Any questions before I shift gears?
I had a question that thanks to the increased number of exoplanets we're finding, you talk about how amateur astronomers are finding exoplanets. So I don't.
Well, they're detecting planets that have already been discovered.
Oh, I see.
But it's very useful follow-up.
Oh, I was about to say, it doesn't sound like the big jump in discovery of exoplanets taken from 95 to present day wasn't exactly from advanced technology, but I was thinking in terms of it's just an increasing interest in finding exoplanets.
Right. And like I said, it's the professional astronomers discovering it, but it is an increase in interest among professional astronomers. The number of astronomers studying and discovering exoplanets since 95 has gone up by an order of magnitude at least.
Well,
So,
with that increase, is there an increasing expectation to actually find a planet that's much like Earth?
yes, especially if the research is NASA funded. That is NASA's target. That is what guides the science. And that's what guides Kepler's mission design. And it's what actually guides a lot of exoplanet research. So if the research I'm doing can help us find that kind of planet, then NASA is interested in planning. So discovering these things, as I said, they're close to their stars, they move around, they're not all in circular orbits. These were surprises. And it really upset our theories of how planets form, where they come from. So we've gotten some hints about what is really going on and where our solar system came from. The first hint came pretty early on. A few people did this, but this is from Fisher and Valenti. The x-axis here represents the iron to hydrogen ratio in a star. So we look at the spectrum, we look at the depths of all of those absorption features. We've taken a logarithmic scale and normalized it to the sun. We're astronomers, so we can't use any kind of simple unit. It looks like sort of backwards and logarithmic. But right here is how much iron the sun has in it, which isn't very much. This is half a dex below, so this is a star with 1/3 the metal content. Irons and carbon and oxygen, we call this metals. We say here, so this is what we consider a metal-poor star. It doesn't have the materials to form planets when the whole thing is getting assembled. And up here we have about 3 times the mass or 3 times the amount of heavy elements in a star. The y-axis is the fraction of stars in each histogram bin with discovered planets. Now they all might have planets, but these are just the ones detected. And what you see is that among stars with a lot of metals in their atmospheres, we discover a planet about 1 in 4 times. And it's very rare to find a planet around a metal-poor star. So this is telling us, maybe not surprisingly, that in order to form planets, you need iron and carbon and oxygen, the things that planets exoplanets are made of when the star is forming. So we believe that, well, we know because we can observe it, and when stars form, in order to get rid of their angular momentum and to conserve energy, which they can only radiate away slowly, they form disks. At the center of a disk is a forming star, and then the disk of material goes out. And we believe it's in that disk that planets form. So if that disk has a lot of these materials, then a lot of planets can form. This is observed. This is the star Beta Pictoris, imaged with a coronagraph. This is a special kind of camera that can block out the light of the star and look at very faint extended emission around the star. This is a young star. It's just formed in the last 10 million years or so, a million years or so. And you can see there's this dust in a disk around the star. Presumably this star, as we speak, in that disk, is forming planets. This is the star Fomalhaut, imaged with millimeter wave emission. And this is the signature you would expect to see if it is surrounded by a ring of material, a ring of dusty material. So the star is right there at the center where the black is, and you can see it should have a ring. You get a lot of emission where you're looking tangentially to the ring, because that's where you have a longer cycle. Inspired by this, some astronomers took a coronagraph, which blocks the starlight, on the Hubble Space Telescope to see if they could see this dusty emission. And this is what they got. The astronomers informally call this the Eye of Sauron image. The coronagraph is blocking a very bright star. Fomalhaut's a naked eye object. Most of these rings going out in the evil iris are incompletely subtracted starlight, because this is a tricky technique. But the dust ring is real that you see going all the way around. So it's not detected very strongly. You can see there's the signal is the ring and the noise in there, but it's clear there's a dust ring that they detected. What's especially interesting is they came back and they imaged this dust ring a second time, 2 years later. And that speckle went, here's the inset, from there to there. And that speckle they can determine, because of the way these images are made, is real. That's an actual bright object sitting next to Fomalhaut. And it went along an orbital path. This dusty ring is all that's left from the formation of some planet orbiting this star. So this is the late stage of planet formation. The planets are basically done forming, and this is just the leftover crumbs that aren't going to last very long. In fact, this dust ring is not circular. You might be able to tell that the location of Fomalhaut is not at its center. The whole dust ring is being gravitationally perturbed by this planet, which helps tell us how massive it is. But its orbit is extremely long. You saw how far it goes in 2 years. This is a very long-term radial velocity project, even if you could do it, which you can't.
Is that scale correct? It's like 100 AU to the planet?
Yes. 100 Earth-Sun distances, it's a little over 100 AU, and that's projected. So there's a geometric effect there, too. We are discovering more and more with coronagraphs, giant planets, sometimes 10 times the mass of Jupiter, out 100 AU from their parent stars. So there's some caveats here. All of the times that's been discovered, it's been in a very massive star. This star is several times the mass of the Sun. They've been found in very young systems. We really don't understand how they got out there, because just like star formation or planet formation theory doesn't tell us how we could possibly form a Jupiter in a 3-day orbit, it also doesn't tell us how we could form something this far out, which should take too long. So we don't know if that theory is just wrong, and it can be done in a way we haven't thought of, or if this planet moved out into its disk. So the new theories that have come around to explain this stuff involve, you can imagine, earlier in this system, before all the planets in it, whatever they are, have formed. First you've just got a lot of dust, and then you get some planets and less dust, and then the theory says actually you should form lots of planets. You should form like 20 or 100 things sort of Earth-based. And then they should gravitationally interact with each other, they should collide with each other, sort of like the collision that we think formed the Moon around the Earth. The giant planets should grab these smaller planets. A lot of the gas and dust will be gravitationally accreted, and the planets basically assemble themselves from the bottom up. Lots of little objects like in dust, and then hundreds of objects, planet massed, and then you end up with just a few objects when you finish, with a little bit of debris like the asteroid belt or something left over, just happened to never quite get caught. These gravitational interactions can move planets around. So this is one way we think that planets can migrate around, is by interactions with all of these forming planets. This is a simulation done by Sean Raymond, a series of simulations, to try and understand if it's possible to have an object with water on it in the habitable zone of a star if the star also has a hot Jupiter. So the Jupiter-massed object must have formed out at 5 AU or something, migrated all the way in. Could there still be a rocky planet with water on it at 1 AU? So at the start of his simulation, this is a numerical simulation he's in, he just created all these little planetesimals, things that will eventually form planets. The red ones are really dry. They're like the moon or Mercury or something. The blue ones and the purple ones are very wet. They're like cometary material, giant comets, basically. And then the big black objects are objects like Saturn or the Sun. And all of the little ones gravitationally interact with the big ones. There are several panels of his simulation. You read it down sort of like a movie, from the start at the top to about 150 million years later at the bottom. The y-axis on each chart is the eccentricity. So what happens is that as these giant planets interact with the planetesimals, they can excite eccentricity. And highly eccentric things typically don't last very long in the system. So here's what the movie looks like. These objects are gravitationally interacting with that as it moves in, but they're also accreting each other. So at the end of his little simulation, he ends up with lots of highly eccentric planetesimals that won't last very long. He ends up with a Jupiter-like object at about half an AU, and he ends up with Earth-massed objects covered in cometary material, big, deep oceans. Pretty close, so the Earth would sit here. So in this simulation, we didn't get anything in the habitable zone of the star with water. But in other simulations he does, he gets them. So in this particular simulation, here's the habitable zone around the star, and there's a little blue dot here about the mass of Earth. So here's a simulation where he successfully generated something like the Earth exterior to the orbit of a giant planet. So what he's arguing is, just because you see a giant planet close into the star, there could still be an Earth-like planet there further out. So it's simulations like these that are telling us how the solar system formed, and really upsetting what we thought we knew about where the Earth's water came from, and where Jupiter formed, and where the Earth formed, and how things happened in the early solar system. I want to show another simulation here by Ed Thomas, who's trying to form these planets from gas. He's starting earlier, when there's just a lot of gas and dust. So this ended up forming 3 giant planets. So there's a gas disk, and then particles accrete, and they form the cores that will become giant planets. And then those cores accrete other cores, and they accrete gas. So the gas in the disk gets just gravitationally bombed on to these things which grow and grow and grow. The numbers are the number of times the mass of the Earth each object is. The blue number is the total mass, and the white number, so 15.3 for this guy, is the mass of rock at the center of the planet. It started, that was the seed crystal upon which all of the seed upon which all of the gas gravitationally landed upon. This is a new way of thinking about planets. Before 51 Pegasi, we would have said that Jupiter is a failed star. It's just like the Sun, it's gas all the way through. It just didn't get enough mass to become either a companion a star on its own. This says no, absolutely not. Jupiter, at one point, was a rocky ball 10 times the mass of the Earth. And around 10 times the mass of the Earth, it started to accrete the gas that was going to fall onto the Sun and make the Sun more massive. And instead, it stole that gas and became Jupiter. So if that's right, then Jupiter should have about 10 to 15 Earth masses of rock sitting at its center, which in principle is a testable prediction, but in practice it's extremely hard to figure that out. The red circles here are the last known position of things that gravitationally were ejected from the system. So you lose planets. Space should be filled with planets that didn't make it. They got into a gravitational fight, lost, and got kicked out of the system. And so we predict a lot of those things as well. Through simulation models like these, Thomas can try and reproduce the solar system and try and figure out what the initial conditions in the protoplanetary disk were. So these are the kinds of things that we learn when you find out that you don't actually know what you thought you knew. And you have to start all over again and say, well, how did we get that extrasolar system? How did we get that extrasolar system? Any questions? The y-axis in all of these is the eccentricity. Oh, I also want to point out one more feature here. You see there's this line of planets like it's a plow pushing those along. That's an orbital resonance. And so this black object here interacts and throws things out, but a planet that goes around exactly twice or 3 times for every time the big guy goes around is actually protected from most of its gravitational perturbations. And so they get a little bit of eccentricity, but otherwise can survive. And it's these sorts of interactions that have saved the material in the asteroid belt. And it's also those sorts of interactions which sculpt Saturn's rings and give them that amazing structure. These orbital resonances with the moons of Saturn. Okay, well that's what I was going to talk about. I'll leave this. One more topic. You may have heard recently about this brown dwarf planet that was discovered. This just came out of Penn State. It's pretty exciting. These are 2 images taken of a patch of deep space by the Hubble Space, the Spitzer Space Telescope. You're looking at infrared wavelengths, thermal emission. Most of the objects here are background stars and galaxies. They're warm, they have thermal emission. The Spitzer Space Telescope can see them. This one says white dwarf. This was a known object. A white dwarf is a corpse of a star like the sun. So when the sun runs out of hydrogen, it'll start to try to burn helium, and it will actually cast off most of its atmosphere. It will grow into a giant star, and then it'll lose that atmosphere. And all that will be left is the core of the star. It'll be about the size of the Earth. It'll be about half the mass of the sun. It'll be very hot. And that's the corpse of the star. So this is a known object like that. And this object here was totally uncatalogued. No one knew what it was. Over the course of 5 years, the white dwarf has gone up and to the right, or down and left, I guess. Yeah. All the other stars stay absolutely still. But that white dwarf, because it's pretty close to Earth, we can see its motion through the galaxy. And this object, which was uncatalogued before, moves in exactly the same way. Which means that these are physically associated objects. This thing is in orbit around that thing. So the Spitzer Space Telescope has detected something, and it's called a cold companion. This is the longest infrared wavelength that Professor Moon could use to look for this cold companion. When he goes to slightly shorter wavelengths, he doesn't see it at all. From that, he can estimate its temperature. Its temperature is sort of like 100 degrees Fahrenheit. So this is a cool object. Now, it's probably about 6 times the mass of Jupiter. It's basically a guess. So it's cooling because when it formed it was hot, and it's older now, and so it's much cooler. So it's not the kind of place that you would go for a visit or something. This is kind of where it's an artist who put it together. There's the white dwarf, and this is the brown dwarf of planet. So we don't know what this is. This could be like that object around Phobos, a giant gas planet. And then when the star died, it's still left over. Or it could be just a failed star. We don't know if there's 10 Earth masses aloft in the center or something. But it's another example of a very strange object. And it's basically the coolest object we've ever detected out in space that's gravitational. Okay. Now.
One of your initial graphics mentioned, about 60% of, stars, seem to be, refined detectable planets.
We have found planets around something like 6% of the stars in the
a lot of that would be restricted by not only the eccentricity of its orbit, but the orientation of its orbit.
We are sensitive. The main limit is the mass of the planet we can detect and the period of the orbit. So if it's a low mass planet, it's hard to see. If it's a long period, it's hard to see. But anything else, basically, we're pretty sensitive to. If you imagine, if our precision is 1%, or 1 meter per second, and we're looking for something like Jupiter. Jupiter has 12 meters per second of amplitude. If it's pitched up by 30 degrees, then you've got half of that. So even at 6 meters a second, you can see it with 1 meter per second precision. It needs to be very close to face on for us to miss it. So we do miss some planets in face on orbits. But you have to be pretty close to exactly face on. And the chances of that are actually small.
Or high eccentricity that is oriented towards you.
Well, if it's high eccentricity, you actually see it more strongly when it's passing near the star.
But the time period could also be much longer.
That's right. So at very high eccentricities, there is a blind spot that gets created if the planet is low mass. So if you... So, if you have this situation, if you happen to miss a periastron here, you might not notice. But if it's a massive star, you can still detect this slight bump. So that really only affects us for highly eccentric planets that are low enough mass that we would not notice this slow rise. And so, yes, that's another way. But for the most part, it's just massive period. Those are our primary arguments.
Okay, so based on the likelihood of finding a planet if it exists,
Yes.
and all the technical details, do you have an estimate of what percentage of stars have planets? Total.
Extrapolate it out. So, look, if we restrict ourselves to planets within 1 AU, so like the Earth, Mercury, Venus, it's at least 20%. If you're
saying 20% of stars have planets like Earth, Venus, or within 1 AU?
Yeah, so we'll say, we can detect something like the Earth, so we'll say, have a planet of some kind. Certainly, have a planet more massive than Earth within 1 AU. It's around 20% at least. If you're willing to go planets less massive than the Earth, like Mercury, and you want to talk about things beyond 5 AU, like Saturn, the number must be larger. So it could easily be 30 or 40 or 50%. Kepler will give us a much better idea of what that number is. In fact, that's one of its primary measures. So that number should come out in the next few years, a good solid estimate. The fraction of stars or planets within their stars' habitable zones is called eta sub Earth. It's the number NASA really wants to know, so it knows how many stars it needs to look at to find planets like Earth in the habitable zone. And that's another number that will come out in the next few years for that.
There was one slide you showed the stars, the metals, and I think it was iron particularly.
Yes.
And I'm not very clear on, you were showing the percentage of iron compared to our star.
Yes. So this is all normalized to the sun.
Right.
So if you look at a star like the sun, something like 4% of those stars like the sun, we have already found planets.
Okay, so yeah, just if you find a star like our star, and then chances of finding, by looking at the composition, chances of finding planets like our planets, is that the idea?
Is that ideal?
Is that the idea? Is that how you perceive to be? I guess since we are looking at the planets, not stars, Earth-like planets, but you're looking at the composition of the planets. You're looking at the composition of the stars,
right?
And trying to see the correlation.
Because this iron and carbon and other elements, you can do this with other elements with the same result. Because that's the material that forms planets, and because the planets in a star form from the same material, this is telling us that planets are more likely to form around some kinds of stars than around other kinds of stars. So if you want to know which stars should I look at to find a star like planet like the Earth, you should look at a star that formed from a lot of material from which a planet like Earth could have arisen.
Okay, thank you.
As a teacher just getting ready to talk to my students about nebular theory, what do I tell them?
About nebular theory?
About how the Earth and the solar system form, since what you're finding out completely challenges what's in my textbook, and I need to start this week.
Sorry.
So, no, it's a good thing, because now I need to know, where do I go, what should I do, should I present both theories, you know? I'm in a quandary here.
I guess I need to know what your book says.
The book says the traditional thing, that the Earth, you know, it started in, and just like we're talking about, how it's the accretion disk and the smaller planets formed and went out like that, and there was never any movement of Jupiter in or out or anything like that.
In the solar system, the best model for how our solar system forms, called the Nice model, brilliant, it works very well. Jupiter did some migration. It moved into about 3 or 4 AU and then moved back.
Okay. Is
And
that NICE?
Sorry?
Nice model?
Nice, yes, Nice, France, yes.
Okay.
And there's not much migration.
Okay.
And so from the pedagogical perspective, I might consider it a detail.
Okay.
They didn't move much, so you are not doing much violence to the science if you just ignore the small.
Okay. That's what I needed to know. But I could then tell them that the solar systems that you're discovering now do not follow that precise. Okay, perfect. Thank you.
I'm sorry, we'll have time for questions at lunch. Let's thank our speaker. And